again, the second time. I see that many of the tourists have left, and only the serious students remain. So I again emphasize this course is addressed to students and not to professionals like Catherine Pepin. And so I will continue where I left off last time. So last time we talked about pseudo reality, this concept of pseudo real. So this could be explained very easily. So suppose you go to a shop or a market and you want to buy a representation, and you want to buy a real representation, and the guy shows you some representation. You can see it's complex because the matrices have complex numbers in them. And the guy shows you a representation matrix, a set of representation matrix, and you notice that it is complex. That D is not equal to D star, so you would reject this as not real. But the guy said it's actually not real. It's true, but it's actually pseudo real. D star G is there exists a S, so that in mathematics this is sort of the next best thing. D star is not equal to D, but it's equal to D up to some similarity transformation. So this is what is called pseudo-real. I think in physics this was emphasized by Wigner. And this turns out to be very important in several areas of physics. In particular, today I'll quickly talk about Cramer's degeneracy. Which is the theorem that for an electron in an electric field, no matter how complicated, each energy level must be doubly degenerate, twofold degenerate. So let me remind the student that degenerate in everyday life is, at least in the US, has a, I don't know in Paris, but in the US, it has a very negative meaning to say somebody is a degenerate. But in quantum mechanics, it's very important. That's when two energy levels have the same, when two different energy levels have exactly the same energy. And this played a very important role in the early days of spectroscopy. I said one electron, but in fact, this works for odd number of electrons, which you could generalize. But I'll just talk about one electron. And the reason for this, that Cramer realized this, was electric field is time reversal invariant. And what does that mean, and how do you see it's time reversal invariant? The easiest thing is to go back to freshman physics, to elementary physics. And if you have two condenser plates, so with some charges and some minus, some charges, then there's electric field between the plates. And if you reverse time, nothing changes. So it's time reversal invariant. Okay, so turns out to be important in particle physics, in condensed matter physics. And so in particle physics, the pseudo-reality comes up, for example, when you discuss Majorana neutrinos and in many other contexts. In condensed matter physics, recently Cramer's degeneracy and things like this comes up in topological insulator, etc. I'm not an expert on condensed matter physics, so I don't take any questions about applications to condensed matter physics, but you have many experts here. So I have to go through this very quickly because it's really, the course is about group theory. Although, as I said last time, this is not a course, again, if you did not come last time, I want to emphasize this again to the students. If you're looking for a mathematics course, this is not the right course. This is strictly a physics course and not a mathematics course. It's about the application of mathematics to physics. So if you want rigorous proofs, etc., this is not the right course for you. Okay, so I want to, but on the other hand, I don't want to spend too much time on the physics. I want to emphasize the group theory. So I'm going to go through the relevant physics very quickly and perhaps a little bit too quickly. So the first remark is Wigner's remark, which is that the time reversal transformation is not unitary. It's anti-unitary or anti-linear, as he said. And Wigner has a long paper, and it's one of his famous paper, etc., etc. But it's very easy to see. Wigner said, in the simplest case, time reversal operator is really like a unitary transformation times k, where k is complex conjugation. So this makes it Wigner calls this anti-linear operator. Mr. Wigner. Okay. When I was writing my group theory book, I looked up I read a biography of Wigner, full of all kinds of interesting remarks. So he grew up in Budapest, and he wanted to study physics, so his father asked him, how many jobs in theoretical physicists are there in Hungary? And so he went to find out, and he came back and told his father, one, and somebody's already taken that job. So his father told him, okay, well, you can still go study physics in Germany. So he went to Germany and came back, but he had no job, so he had to work for his father in the leather factory. So he told himself he doesn't want to spend his whole life working with leather. So one day he found an opportunity and so on and so forth. Anyway, very interesting story. So Wigner's remark is the following, that when you study quantum mechanics, suppose the Hamiltonian is time reversal invariant, then you see that time and I appears in this combination. It's very strange. So this is just heuristic. This is, as I said, I don't have time to do a rigorous argument. This is hand-waving argument, so very hand-waving. The hand-waving argument is that if you like t goes into minus t, right, then in order to keep this invariant, I must goes into minus I. So that's why you need a complex conjugation, an extra complex conjugation, which makes time reversal very, very peculiar. For example, in quantum field theory, time reversal operations always a very peculiar. It's completely different from, it seems different from charge conjugation and parity. Okay. Then the next question is, what is U? And this is something you have to work out case by case. So for example, we have half spin 1/2, which we talked about last time. Then it's represented in terms of Pauli matrices like this. Okay. And what we want, this is what we want. We want S goes into minus S. So this is how we will choose a U such that this is true. This is what we want. Okay. We want S to goes into minus S under time reversal, right? Spin is spinning like this. So if you reverse time, it spins the other way, right? So that's sort of almost high school physics. And so under time reversal, this thing goes into a 1/2 psi dagger, k u dagger, sigma u k psi. Okay. Now, the claim is that we can get this if we choose u to be eta sigma 2, where eta is some arbitrary phase. So if we plug this in, we see that this is u is eta sigma 2, u dagger is eta dagger sigma 2 dagger. So it's eta star eta k u k sigma 2 sigma 2 psi. Sorry, I'm just doing this part, k. But remember, we told you that Pauli matrices anti-commute. So, so for the this thing goes into, this is equal to minus sigma 1, sigma 2, plus sigma 2, minus sigma 3. So sigma 2 anti-commutes with sigma 1, and it anti-commutes with sigma 3, but of course it commutes with itself. So you have this peculiar sign minus, plus, minus. But this k, and Mr. Wigner was right, and of course he has to be right, since he's a famous person. And so k is complex conjugation, and last time we pointed out that of the 3 Pauli matrices, sigma 2 is the only one that is pure imaginary. Sigma 1 and sigma 3 are purely real. So the complex conjugation, when it comes through here, it kills this other k, but it changes sigma 1, sigma 2, sigma 3. So it changes the sign of sigma 2. So you get minus sigma 1, minus sigma 2, minus sigma 3. This phase, of course, is by definition 1. It's a phase factor. So you see that this is precisely, you get s goes into minus s. So this is a poor man's way of showing that if you choose u to be this, then this time reversal works. Okay? So okay. So can I erase this now? Yes. No free lunch today. Yeah. Oh, I see. I see. Oh, thank you. Okay, so now this is just background, and now we prove Mr. Cramer's degeneracy. So here's the proof. Okay, the proof is a little bit tricky, but it's once you understand how to do it, it's simple. The proof is what Cramer's did, Mr. Cramer's, is to study t-square. What happens if you act with time reversal twice? Okay, you time reverse, and then you time reverse again. So intuitively, you think that if you take time, the flow of time flowing like this, and you reverse the flow of time, and then you reverse it again, you should get back to the identity. You should have reverse time, and then you should have done nothing. But Mr. Cramer's discovered something interesting. We just said that t is given by this, so t squared is given by that. Okay. Now, you see k is going across the eta. It turns this k going past eta turns the eta into eta star, and it turns sigma 2 into minus sigma 2, and then it annihilates that k. So now we have eta times eta star, which is 1, since it's a phase, and then sigma 2 times sigma 2 is 1, so we get minus I. So this is one of those subtle things about quantum mechanics. It seems very simple, but if you cannot sleep at night, like I often cannot sleep at night, you think about this and what it means. And it's very difficult to understand, why you reverse time twice and you get a minus sign. Okay. So this is the basis of Cramer's famous observation. This made him famous forever. If you discover something like this, it would be great. Okay, any questions? Okay. Yeah. Well, minus the identity. Yeah.
What does it mean in the reality?
Well, it means the wave functions multiplied by a minus sign. Okay. In quantum mechanics. Yeah. Well, if you're spinning something like this, you make a movie of top spinning, then you reverse the movie, the top would be spinning this way. Okay. It'll be spinning the opposite way. Yeah. It's what? No, it's freshman physics. It's not, you don't need any group theory or quantum mechanics or anything. Just a spinning top. Momentum reverses, right? And so since angular momentum is x cross p, since momentum reverses sign, but not space, then x cross p reverses sign. Yeah.
Is this related to the fact that S is a pseudo vector?
Okay, I try to avoid learning as much jargon as possible, so I think it is related to that, but if I remember what pseudo-vector is. I think I vaguely remember something called axial vector, which is the same as pseudo-vector, yeah. But that's usually regarding parity. I usually tell my students not to learn any jargon because the brain is a finite size. Okay, any other questions? Yeah, yeah. Oh, okay. So now so the proof is yet to come. This is just lemma. So here's the proof. So T psi, if I act with time reversal on the wave function, there are only two possibilities, right? Either it is psi, of course could be up to a phase, or not. That's at least binary logic. There's only yes and no. There's no maybe. So if we assume this, let's assume this, that T psi is proportional psi. So T psi is some phase factor times psi, where alpha is some phase factor. Okay, so we assume this is our assumption. And then we act with T on this again, T squared psi, which is T e to the I alpha psi. But T acting on e I alpha psi, when it goes past the e to the I alpha, because there's a complex conjugation in it, it turns into the e to the minus alpha T psi. Okay? But T psi is e to the I alpha psi, which is equal to psi. So Mr. Kramer's found a contradiction, and so it's proved by contradiction. Therefore, T psi cannot be proportional to psi, and so means that there are two states that are degenerate. Okay. So as I said, this fact is important in, of course, also important in atomic physics, which is how Kramers originally discovered this. Okay, now last time somebody asked me a question, I've forgotten which student. I asked a very good question about determinant, but I answered it probably too quickly, so I like to go back to it again, to the student's question. And this is a good place to talk about it, because the pseudo reality of the so what we discover here basically is that the defining representation of SU2 is pseudo-real. By the way, I always find Kramer's degeneracy very beautiful. It's really this this is what makes me interested in physics and mathematics. You know, there's some very statement which is simple but deep about mathematics that somehow SU2's defining representation is pseudo-real. You may think, okay, who cares? Real, pseudo-reals are the same. But it actually has physical significance. It makes very important physical significance. And that no matter how complicated the interaction is, as long as it's time reversal invariant, the levels are doubly degenerate. Okay, I find this really quite amazing. So I'm going to talk about this again. Last time I talked about it. And you remember that for SUN, I said that the defining representation is psi I, and then the conjugate representation is just the complex conjugate. And very clever people that are much clever, very clever people, I don't know who, invented this notation that instead of writing star, we write a lower index. So upper and lower indices. And they transform differently in general for SUN. But SU2 is special. So why is SU2 so special? Because the epsilon symbol has two indices. In general, so I want to emphasize this here. For SUN, the epsilon symbol have n indices. And I find that this is worth emphasizing because sometimes students forget. And because I first learned it as this anti-symmetric symbol for SO3 for rotation. So for a long time I thought the epsilon symbol should have three indices because for rotation it's epsilon ijk. And only later did I suddenly realize that it actually, the number of indices changes with the group, with the algebra. Now, SU2 is special because epsilon has two indices. So therefore, if I have psi I can multiply this by epsilon ij, and I could define this as phi I. And phi I would then transform the same way as psi I. Okay? And if you are really poor man, as I said, I like the poor man's approach to doing things. The poor man would write everything out in terms of components. Then phi 1 is psi 2. I'm sorry, j. Phi 1 is something like minus psi 2. And phi 2 is plus psi 1. So you see that it's just taking the two components and flipping them with a minus sign. Okay. And now you recognize this is precisely what the sigma 2 is doing. The sigma 2 in the time reversal. So pseudo-real and time reversal, they're all related in this way. Now, I come to the question that the students asked me about the anti-symmetric symbol and the determinant. So I did not really, I answered the question very briefly, but it's worth writing it down. It is really an identity for the determinant for n by n matrix. Any matrix M, there is a determinant identity about the determinant, which is that epsilon I1, I2, In, M, I1, I2. So it's a matrix, so it has two matrix, so it's two indices. I write one index as I, the other as J, I2, J2, M, I3, In, Jn. That this is equal to the determinant of M, epsilon J1, J2, Jn. Okay? So this you should have learned in school. In fact, on the definition of determinant, how you calculate determinant. And this is called Cramer's formula. Okay. So if I give a group theory course, the first exam question would be, is Cramer and Cramer the same person? And the correct answer is that no, they're different persons. Okay. So when I was an undergraduate at Princeton, I once took a mathematics course, and the math professors gave 10 problems on the final exam, and you only have to do one. But if you look through the list, you would see that one of the problems is very easy. It's probably something like, is Cramer and Cramer the same person? Or something like that. And then after the exam, he reviewed that the other 9 were all unsolved problems in the field. And so he was seeing if any students are either intelligent enough or stupid enough to have done one of the other 9 problems. So this is the... Okay, so this is a very important fact to know, and this is underlying all this. So you can verify, so it's exercise. You should verify verify this and then verify that. And you see that the statement that this transforms the same way, okay, follows from this identity. And you can also see how this determinant, the easiest thing is of course try for 2 by 2 matrix. You see that it's just anti-symmetrizing the m's and you get the determinant. Okay. So Guida very kindly sent me a paper. He he actually looked up the paper of Levi-Civita and Ricci, right? They wrote the paper together. So that was the claim was when the anti-symmetric symbol first appeared in physics and math. It's sort of surprising it appears so late in mathematics. Okay, so so this identity you see applied to SUN is very special because for a element of SUN, the determinant of U is by definition equal to 1. And this is what the S means. The S means the determinant is equal to 1. So if I apply this to the identity epsilon I1, I2, In, U I1, J1, U In, Jn, the determinant is 1 by the definition. So the anti-symmetric symbol has this nice property that it moves, if it's transformed by the U's, it remains the same. And this is why it's called the invariant symbol. The anti-symmetric is an invariant symbol just like the Kronecker delta. And last time I mentioned that it's probably, if you want to keep everything clear in our mind, some people call this invariant tensor, and I think sometimes notation terminology confuses people also a little bit. So I prefer to call it a symbol, because this is not really a tensor. It's the epsilon. It's just a bunch of zeros and ones and minus ones, okay? So I think people that call it tensor sometimes confuses people. So similarly, here I've done everything for the anti-symmetric symbol with upstairs, downstairs indices, but of course we can do it for upstairs indices. Okay. Yes? Oh yeah, okay, please remind me. And I was hoping to move to a different room. Okay. So is this better? Yeah, thank you. Okay. So now the next thing I'm going to do is I'm going to study. So in some sense, so far I've spent half an hour just finishing the last lecture. Today's lecture is actually, we're going to start doing the Lie algebra of SU2, which we know is isomorphic to SO3. The algebra at the algebra level, locally isomorphic. And the reason that this is important is because this course, as I said last time, I want to focus on the Cartan classification, and then on the Dinkin diagrams. So this is prototype of Cartan classification. So if you understand the Lie algebra of SU2, SO3, you've taken the first step towards understanding Cartan classification. Okay. So we could be doing either SU2 or SO3. And now, what do I do? Maybe I'll just erase this. Sorry.
So we already, no, you want this one.
Oh, okay. Thank you. Okay, thanks. Okay, so thank you very much. So you know that I assume that everyone here has studied angular momentum in quantum mechanics. Okay, I assume that that's true. If you haven't studied it, it's not a problem. You should just go home and study it. Okay. So there's always a cure for ignorance. So, in fact, I saw that Obama gave a lecture yesterday at Rutgers University about ignorance, and he was talking about another person. That so, but anyway, in physics, ignorance is easily cured. You just go home and read a textbook. Okay, so I assume all the students here know angular momentum, right? So angular momentum in quantum mechanics, if given by three generate operators, and they satisfy. So I sometimes I write it Jx, Jy, Jz, but also sometimes it's J1, J2, J3. And the commutation relation is Ji, Jj equal to I epsilon I Jk, Jk. Okay? So this just means cyclic Jx, Jy. So for students who are not so familiar with this, let me just say this, it just means everything is in a cyclic Jx, Jy, Jy, Jz is equal to Ijx. Okay. So this is also clearly represented by the Pauli matrices. So for angular momentum, we use J for, okay, I'll just stick to J. So the treatment of angular momentum in quantum mechanics is very, really very beautiful. And the trick is to go from Cartesian to polar coordinates. So you define J plus or minus as Jx plus Ijy and Jz. So at this point, I don't know how much I need to cover this, working out. So I'll just give a quick sketch. Only the students, all the students know about angular momentum in quantum mechanics? Most? Yeah. Okay. Good. This kind of pole is always very, that's how you know how the poles could easily be wrong. Because when you do the pose like this, all the people know it, not their heads, but the people don't know it, don't do anything, don't say anything. So I'll go through it very quickly, but because it's important, because we're going to use it in Cartan classification. Okay, so the algebra is then generated by J plus minus Jz, and here's the algebra, J. So I'm just going to follow my book at this point, okay? And Professor Gugula said he was going to provide the students with copies or something. Already done. Oh, good. Oh, okay, okay. But not today's material. Yeah, since you don't know what I'm covering. Yeah. Okay. So this is on page 204 and following. Okay. So. Okay, so if you rewrite this algebra, just rewrite this in terms of J plus or minus and Jz. We have Jz equal to J plus or minus equal to plus or minus J plus or minus, and then J plus J minus is 2Jz. So we could diagonalize Jz. We can choose one of the three operators to diagonalize. So Jz, so we can write it in terms of its eigenvalues. and eigenvectors. We call the eigenvalue m, and we it's easy to show that m is a real number, and the eigenvectors little m, using the Dirac-Brown-Ket notation. So then the famous thing is to ask, if I act with j plus on m, what is this thing? And I think all the people who know that this you work out by the algebra. You commute j, z, and j plus the commutator of j, z, j plus acting on m. Okay, and this thing is j plus, therefore this is, and jz acting on m is m, so this j plus, so you factor this out, it's m plus 1, j plus m. So you made a great discovery here, that j plus acting on m, therefore j plus acting on m is proportional to m plus 1 with some constant to be determined, which I call Cm plus 1, to be determined. Okay. And similarly, we conclude that j minus, we can ask what j minus of m is by calculating jz j minus m. And here I let this be an exercise for the students. You find that j minus m, not surprisingly, is m minus 1, and with some constant, which is also to be determined, which we call b of m minus 1. Okay? So this is the famous ladder, and that was worked out by, in the early days of quantum mechanics. Some people call this a ladder. And you can see that the states are, if the state here is m, then we act with j plus, we go to m plus 1. And we act with j plus, we go to m plus 2 again. And we act with j minus, it comes down. And so we act with j minus here on the state m, we get m minus 1. And so the states form a ladder. Okay. So I'm going to skip over some details. For example, you can easily, as an exercise, you can show exercise. So especially the students who have never seen this should do all these exercises. That, for example, you can find that B and C are related, okay, and so on. Now at this point, we we have to input a famous theorem, which is that for compact groups, which is I'm not going to cover, it's in the first part of the book. When you have a compact group, the representations are finite dimensional, so there are only finite number of states. So therefore, we know the ladder must terminate. So at some point, the ladder must end. So there must be a top rung here, and this top rung we're going to call J, okay, little j. Oops, I guess you have to raise this one first. Okay. Okay, so now this is important because you will see that Cartan classification is just generalization of what we're doing here for SU2. You see it just it generalizes, but in a highly non-trivial way. Okay. So we have, since we said the ladder must terminate, there has to be a highest rung, which we call J. When what does that mean? That there's a highest rung. That means if we act on J plus on J, has to be 0, because there's no J plus 1. By definition, by assumption, J is the highest state. So when we act on it, you get 0. Now at this point, you notice that we've only, a stick would be useful here too. We have only used the first part of the algebra, the commutation relation between Jz and J plus or minus. But we have not used the second commutation relation, okay, which is J plus J minus commutator, okay, is equal to 2Jz. So now let's use this. So from here, we write J minus J plus acting on J. We know is 0. But J minus J plus is J plus J minus minus 2Jz J. Okay? But J minus acting on J is C. Up there is J minus is this B, but then we prove that B is related to C. So if you work in this very carefully, you would see that this piece is Zj absolute value square, and this is minus 2, and Jz acting on this state is by definition equal to J. Okay? So therefore, we determine Cj. So Cj square is equal to 2J. And now we use this commutation value, this thing again, by sandwiching it between M okay, and this is M J plus J minus minus J minus J plus of M. So again, using the definition of C, we see that this is Cm square minus Cm plus 1 square. I'll let you work this out. But this commutator is 2Jz. Okay, so this is 2m. So this gives a recursion relation. This gives a relationship between Cm plus 1 and Cm. And so this allows you a recursion relation. And so you could just keep on going. So in particular, Cj minus 1 square is Cj square plus 2J minus 1, which is then 2J minus 1. And so on. And I won't bore you. You can work this out yourself. And so on. And you keep going. And you discover that Cj minus S, minus after S steps, you discover that this is S plus 1, 2J minus S. Okay? And so you keep going down. So we assume the ladder has a maximum, has the highest rung. But if you keep going, you see that the ladder at some point must reach a bottom rung, okay, the lowest rung. So the lowest rung is reached when 2J minus S vanishes. This is positive, so it's when 2J equal to S. So after S, 2J steps, S is the number of steps. After 2J steps, it ends. Okay. Well, so the big surprise, so you get the representations of angular momentum, but here's the big surprise. If we are doing SO3, and angular momentum for the rotation group. The big surprise is that when S is equal to 1, there's also a solution for J equal to 1/2. So now we understand, strictly speaking, mathematically, the group SO3 does not have a half integral representation, but because we understand that SO3 is locally isomorphic to SU2, as I explained last time, and SU2 double covers SO3, the algebra of SU2 has a half integral representation. Okay, so now from the so in this case, you know what the matrix element of J plus and minus and JZ is, because there are only two states. The ladder has only two steps, plus and minus. So the ladder has just two levels, plus and minus, and J plus takes you up, and J minus takes you down. And so these are then represented by 2x2 matrices. And exercise for you to work out is that, of course, you get the Pauli matrices. And as I said last time, Pauli matrices, of course, were known to mathematicians, in particular to people like Sylvester. Okay, any questions? So it's almost time to take a break. I'm sorry that I follow my book. So, but I think many students indicated they've seen this. Okay. All right. So my next topic is. Oh, sorry, I didn't raise this again. People, I guess, have trouble seeing this. Maybe I'll do this. So we'll take a break soon. So I'll finish SU2 shortly, and I hope that today I will get to, in the second half of this lecture, get to SU3. And from what I could cover, it looks like maybe next time we could start on some of the Catan classification. Okay, so 1932, Chadwick discovered the neutron. Okay, and he discovered that the mass of the neutron minus the mass of the proton divided by the mass of the neutron, the fractional number 939.6 minus 938.3 divided by 939.6, and this is 0.00138. Now this is actually, in my opinion, one of the most important small numbers in physics. Okay, it's not emphasized enough. Because of this number, Heisenberg and also others, this is very typical in physics, when several people did the same thing, and in fact the others did it before Heisenberg, but we only would say that Heisenberg did it. Proposed that the proton-neutron are somehow related by an SU2 transformation. So under this group, the proton-neutron form a spin 1/2, the 1/2 representation. And because this is, the mathematics is the same as spin, this became known as isospin. So at first, of course, the main name is much longer, but later shortened to isospin. Okay. Now, why do I say this number is very, very important? Because to me, it's extremely important. I wrote a book about symmetry called Fearful Symmetry, a popular book. And in the history of symmetry, until Heisenberg, until his paper, when we talk about symmetry, it was always space-time symmetry, right? Rotation, translation, and then Lorentz invariance, Einstein special relativity, and so on. It's always the symmetry of space-time. The other thing is that up to that point, all the symmetries of space-time is exact. Up to this day, everybody assumes and believes that the rotation invariance, for example, is exact in the fundamental laws. But this opens up really a new concept, which is symmetry, which is not exact. But even more important, it opened up the whole concept of internal symmetry, that the world has some internal structure outside of space-time, and that group theory and symmetry is important, and that group theory is relevant. And this, as you know, led to gauge symmetry, gauge theory. So which is of course still developing. Yang-Mills theory and so on and so forth, SU2 cross U1, and onto grand unified theory and string theory and so on. So this number, I think, is one of the a number that people don't talk about, but very much. But I think this is really an extremely important number. Now, the truly remarkable thing, and in my books I always talk about nature's kindness to physicists. So nature is very, it's almost sending a signal that to physicists at least, not to mathematicians. Mathematicians, of course, study mathematics, but in physics we study physics, not mathematics. That the remarkable thing, nature is very kind to us, because it first showed us the spin 1/2 electron, which we said last time was a shock to physicists, right? I mean, introduced by young people, Gauss-Schmidt and Uhlenbeck, and also Kronig, whom we remember before he was talked out of it by Pauli. But with the spin 1/2 electron, physicists already knew SU2. So the remarkable thing is that there's no need to learn new math, new group theory. So the SU2 is already there. And now I emphasize that this immediately led to a lot of predictions. For example, that particles, Heisenberg, is that particles should form representations of SU2. So in 1947, the pi plus or minus meson were discovered, the pi plus and the pi minus. Okay, so Yukawa had a theory and so on, but I won't go into the details. The proton is supposed to go into neutron plus pi plus, and the neutron is supposed to go to proton plus pi minus. But we already know how to multiply angular momentum. We know how to multiply representations together. This was called the addition of angular momentum in quantum mechanics. Okay, so right, so we know how to multiply isospin immediately without learning any new math. So you sorry. So we know how to multiply. So we know that this is, according to Heisenberg, it's in the spin 1/2 representation, isospin 1/2. And what is the isospin of the pion? So we don't know, I pi, okay? And so, but this has to contain the isospin 1/2, because by definition the proton and neutron are both 1/2. Therefore, but we know that when we multiply angular momentum, the representation you get is I plus plus a half, or I pi minus 1/2. Okay? So I pi could only be, there are only two possibilities. I pi is either 0 or 1. But 0 is already not possible because you already discovered two pions. Okay. Pi plus and pi minus, so it has to be pi 0, pi 1. But from SU2 or from SO3, from angular momentum, you know that the representation for one, if you have the representation J, the dimension is 2J plus 1. That's, of course, a result that we just derived on this blackboard, but which I did not emphasize. So you know the representation 1 has 3 states, contains 3 states. Therefore, if you only know the pi plus or minus, so group theory gives a very powerful prediction. It predicts that there must be 3 pi mesons. There must be 3 pi mesons, and the other one, if you work it out, has to be a neutral pi meson. So it was predicted by group theory, and this was discovered in 1950. And the reason that it's discovered 3 years later is, of course, it was much more difficult to discover experimentally, to deal with a neutral particle than a charged particle. Now, notice a remark here is that when Heisenberg proposed SU2, that was just a guess. So that's what makes him such a great physicist. Because other people have said, okay, the proton and neutron have the same mass, so an obvious symmetry would be interchange symmetry, that you can exchange proton neutrons. So in modern language, it would be just a finite group Z2, exchange of two things. Okay? So, but obviously, SU2 is a lot more powerful than Z2. If you only assume Z2, interchange symmetry, like some of the other people, they have no way of predicting that there's a third pi meson. Okay. Okay, so maybe we should take a break here, but last time I told a lot of stories, and since I'm in Paris, this reminds me of a story. The name meson, which is now universally used for pi meson and so on. As you know, meson was introduced by Yukawa. And so there was a long, complicated story involving many languages. Because in Chinese and Japanese, the particle that mediates, somebody who suppose you introduce your friend to another friend, the Chinese character is this. So Yukawa used this, and so that was why it becomes known as the pi. Okay. So this is not known in the West at all. It's only known to Chinese and Japanese speakers. Now, the other thing is that the original name was mesotron, as some of you probably know. But then, of course, this American tendency of shortening everything to all the long words into shorter words. So it was called meson. Everybody calls it the meson. But the French objected vigorously. So they absolutely mounted a tremendous campaign to forbid this word in physics. Because the French said the students will all be confused between this particle and their house. So, this is obviously very silly, but eventually the French had to give up since everybody uses meson. Okay, so on this joke, we'll come back in 10 minutes?
Yeah, 10 minutes.
10 minutes, okay. By the way, that's really true. The French objected. So thank you for coming back. I'm not sure in you twice already. So in California, the students may not come back. I don't know. Sorry? Two-time reversal, yes. In fact, this is a serious question, actually. Because some of my books are so thick, I asked the publisher to divided into different volumes. And like Weinberg does that, Weinberg's field theory in 3 volumes and so on. So I want to cut all my books into smaller. And my editor, Ingrid, at Princeton University Press, well, she always tells me, Ingrid always says, the trouble is that if you cut it into 2 volumes, people only buy volume 1 and then they don't buy volume 2. So this is the same as whether people come back to the second half. Yeah. So the probably the strategy is to put all the jokes into volume 2. So, okay, so during intermission, there were 2 questions that people asked me. They were very good questions, so I just like to repeat it. Maybe the logic for Cramer's degeneracy is not very clear. And in fact, when I was a student, I was confused by Cramer's degeneracy also. The way Cramer's reason is like this. He actually said, so if time reversal, if the Hamiltonian is time reversal invariant, then T psi, time reversal, T acting on psi, has to have the same energy as psi. But then the question is whether they're the same state or not the same state. Okay? So that's the, I guess it was erased. T psi, is it the same? It's not the same. Okay? So it's a kind of Shakespearean question. Okay? To be, yeah, whether T psi is the same as. So what I showed, or what Cramer showed, is that T squared is equal to, T psi cannot be equal to psi, because otherwise T squared should be equal to minus psi. Okay, so that was the contradiction. Okay, so that's where the degeneracy comes from. It was not clear, yeah. So T psi cannot be the same as psi. Now the other question that was asked me was that about isospin, so perhaps that's also not very clear. What Heisenberg said was the following. He said, look at this number, it's very, very small. And so I can imagine a world in which there's no electromagnetism. So he said maybe the only difference between proton and neutron is just that proton is electrically charged and a neutron is not electrically charged. Okay, so if I imagine a world in which there's no electromagnetism, then they should be the same. So in that world, isospin would be exact. Okay? But in our world, isospin is not exact. But the effect of it being broken, of it not being exact, should be very small. So that's why I say this is a very small number, because you expect the corrections to isospin, to the predictions of isospin, should be governed by this very small number. But this prediction, because it's just something exists or not exists, is yes or no, is not subject to this approximation. So this is a sort of Heisenberg's, this is why this is very important. And Heisenberg's thinking, as I said, is now used everywhere. You just imagine that we live in a world in which some symmetry is exact. Okay. So electric charge, imagine a world in which there's no electric charge, only strong interaction, then the proton-neutron will be the same. Now, in fact, talking about electric charge, there's also something quite interesting. And this was perhaps Mr. Heisenberg had some trouble with his contemporaries. And this is also I gave the students a lesson last time, is that if you have a good idea, you shouldn't worry about the objections that people have. Like if you thought of electron spin, don't worry about the people that said the surface electron is faster than the speed of light, stuff like this. So Heisenberg's also, the objection that people had is that, look at this sign is plus, okay? So that means the neutron is actually heavier than the proton. And so Heisenberg, you're talking nonsense, because proton is charged, it should be heavier, okay? So, because there's electric energy, we all know that, and so on and so forth. And furthermore, I think people in the 30s also pointed out if the proton were heavier, then the proton would decay into the neutron rather than the neutron decaying the proton. We know the neutron decays into the proton in 10 minutes or so by beta decay. But if the proton decays in the neutron, our universe would not be very fun because all the hydrogen atom would decay, the proton would decay into neutron, or the electron would fly off, and there'll be no atoms, and so on and so forth. So even when I was a student, there were people writing papers trying to explain why neutron is more massive than the proton. And people that written a more or less reasonable paper were given professorships at Princeton and places like that. And turned out, of course, later these papers are all nonsense. And we all know that now the reason the neutron is heavier than proton has nothing to do with, has very little to do with electric charge. So anyway, but that was the first time, in fact, the first time I made some money was that, and it was also involved, in fact, a Frenchman, right? Is Maurice Jacob French or is Swiss? Jacob, Maurice Jacob. He's French, yeah. So the first time I made some money was even offered to me by some Frenchman. I was in Boston at the time, and he came to Boston, and my girlfriend and I took him hiking. And then while hiking, he told me he was going to start a new journal. And of course, for me, I was just a graduate student. So at that time, he seemed very old and very senior and so on and so forth. But anyway, he said he was starting a new journal called Physics Reports. And he would give me $500 if I would write an article about why the proton is heavier than the neutron, or the other way around or something. So I wrote an article and gave me $500. So Henri Hollande here is an editor for Physics Report, and he told me the other day they now pay $700. So after 40 years, the rate of increase is almost almost nothing. Okay. Anyhow, okay. So, of course, my sons were crazy about Maurice Jacob because his daughter is a famous actress and so on and so forth. So I met her when she was a little girl. So yeah. So I'm not going to read from this book anymore. So for the rest of this lecture, so I can give it for people to look at again. Okay. So the electric charge is a bit of mystery, and you notice that the electric charge for the pi meson, pi minus, pi 0, and pi plus, which belong to isospin equal to 1. So you see Q for, it's just I3. It's just the third component of isospin. So just like the third component of angular momentum, I3 is equal to plus 1, 0, minus 1. Okay? But now you see another mystery, which is the proton and neutron, which is I equal to 1/2. The charge is not right. I3 would be plus 1/2 for the proton, minus 1/2 for the neutron. So people have to introduce a hypercharge. And I think this was introduced by Gelman and Nishijima. And the notation is Y. And this played a very important role later in Weinberg's SU2 cross U1, the electroweak unification. So where, by definition, Y is equal to 0 for the pion and equal to 1 for nucleon. For the pions and for the nucleons. So you realize that the physics students should realize that this is not an explanation of anything. So I don't know why. It's just a rule. So it's just I don't know what you call it. So I don't know how these people become famous, Gelman and Nishijima, for writing down this formula. I mean, it's not an explanation, right? I mean, but later, when we go to SU3, we'll see that this is a comes out naturally of out of SU3. But remember this convention that physicists use, that is 0 and 1, the hypercharge. And unfortunately, this disagrees with Cartan's normalization. So The difference is some square root of 3. So all the formulas later would have some crazy square root of 3. So you have to remember that's the origin of the square root of 3. Okay, now I wanted to, since I really like group theory, I want to emphasize the power of group theory. It's amazing. I'm always amazed, and also theoretical physics, of course. So, there were two reactions that you can measure. A proton colliding with proton forms a deuteron plus a pi meson, pi plus. And the deuteron, D, for those of you who do not know, it's a bound state of proton and neutron. So just a proton and neutron loosely bound together. Okay. And it has isospin equal to 0 because experimentally the proton-proton is not bound, does not exist, and neutron-neutron is not bound. Only proton and neutron. So we know it does not have, it forms a singlet. So it's under isospin, it's equal to 0. And then another reaction was measured, which is, this is proton plus neutron colliding forms a D plus pi 0, okay? Now, the power of isospin, power of group theory, is that you can use group theory to relate these two processes. So you don't know anything about the strong interaction. The process is very complicated. You don't even know what the Hamiltonian is. You just know the Hamiltonian conserves isospin. So you can predict that the ratio of these two cross-sections is 2, according to group theory, okay? So the exercise is to calculate 2, okay? So this is a very beautiful application of group theory, and I believe it was done by a famous person. It was first done by Yang when he was probably just a student. So this process was measured in 1951, and this is 1952. This is a more difficult experiment because of the neutron. And within the experimental error, it's almost exactly 2. So it was a very striking verification of isospin. And then, of course, there are hundreds of other experiments. Now, I'm always amazed when I talk to my colleagues and talk to students about the power of theoretical physics, because my experimental colleagues in the physics department, you know, they want to measure something like proton plus proton to D plus pi 0. First, they build some accelerator, you know, not the LHC, but some cyclotron, and you go down to see the cyclotron, you see all these wires and vacuum pumps and all the detectors and so on. And they spend 2 years measuring this thing. And then another group spent 2 years measuring the other reaction, then they divide one by the other, they get 2. So group theory, I'm always amazed that theoretical physics actually works. But this is why we're in this room, because theoretical physics works. Okay. Sorry?
The conclusion that there is a reality.
There is a reality, yeah. There is a design. Yeah. So this is why, anyway. So SU3, now the next topic is SU3. So now we go from SU2 to SU3. So, by the way, for students who are seeing this for first time, you cannot learn group theory or physics by just listening to things. You have to sit down and calculate the two, okay? See if you can calculate the two. So SU2, so now we finish with SU2, and SU3 appears twice in particle physics. Of course, it also appears in other areas of physics, which I will mention, other areas of physics also. Okay. But it interestingly appears twice, as you know. It appears in the early 1960s, and that's Gell-Mann, quarks, etc. And then it again, a second time, in early 1970s, which is QCD. So, but two completely different SU3. So, now in group theory, smaller groups often have very special features. And so there's sort of a little bit paradox, or more features, I should say, than the large groups. So this kind of almost paradoxically, so when you study group theory, the smaller ones are actually more difficult to understand. The bigger ones are actually easier. Because for SU2, for example, there's all kinds of features like isomorphism, locally isomorphic to SO3. And you wouldn't have, you have something very special with these small groups, but not for example, you don't expect SU21 to have something special, or SU217 to have anything special, right? But SU2 has some special features. And one reason, and it's, for example, pseudo-real, its defining representation, which we see is because of the epsilon symbols, okay? Now, in fact, both of these features have something to do with pseudo-real. But now we go to SU3, so there's less interesting features, but there's still something to do with the epsilon symbol, because now the epsilon symbol has 3 indices. Okay, so now we see the psi I, which is a 3-dimensional representation and written as 3, and psi I is no longer pseudo-real, not pseudo-real. This is not equivalent to not equal to the psi I by similarity transformation. Okay, so this is distinct. The conjugate representation is really distinct. Okay, so that's because the epsilon symbol has 3 indices. So you remember for SU2, it's because psi I and psi I can be related by epsilon ij psi j. So this thing is really distinct, and it's called, the representation is called 3 star. It's the conjugate representation. And in fact, in particle physics, to use language, this is the quark and this is the anti-quark. And so it's the deep statement. The anti-quark is not the same as quark. They're really different. If you like, there exist some other quantum numbers in the world. Now you see that this all follows from the fact that you have 3 versus 2, very amusingly. And I'll write it over here. Because suppose you try to play the same trick as for SU2, you take psi I and I say, okay, I multiply by epsilon ijk and define it as a new object. Let's call it psi jk. But now you see, oops, this is not the same as psi I. This has 2 upper indices. So the same trick that works for SU2 does not work for SU3. Okay. So in SU3, you really have to have 2 kinds of indices, upper and lower. Is that clear? There's a huge difference between SU3 and SU2. Which is related to the pseudo-real and Majorana, the existence of Majorana, and so on. And it's kind of a very interesting feature that the Lorentz group is related to SU2 and not so, well, it contains SO3. But anyway, that's a different story, how Majorana particles could arise. Okay, so now, so you see for SU3, then you're forced to introduce, you cannot get away from not introducing upper and lower indices. So the most general tensor, the most general representation would have m upper indices and n lower indices. And so this is called m comma m. That's the notation. So m indices, m upper indices, and n lower indices. So for SU2, you don't have to worry about lower indices at all. Okay? And but there's still one simplifying feature. Which you, again, thanks to this anti-symmetric symbol. Using the anti-symmetric symbol, and I remind you there are two of them, using the anti-symmetric symbol, we can take all the upper indices to be symmetrical, okay, and all the lower indices to be symmetrical. Symmetrical means if I interchange I2 with, say, I7, I1, I7, I2, IM, this is the same. And similarly, with the lower indices, okay? And this is because we have the epsilon symbol. Okay. So I'm going to prove this theorem. So this is a very fundamental theorem for SU3. Why is that? So this is not true of SU4, SU5, and so on and so forth. Okay, so let's prove it. The proof is by induction, or iteration, or whatever you call it. I guess induction. Proof by iteration. Actually, that's what I wrote down. So we want to study the representation of SU3, and since it's represented by two integers, we can put it on a lattice. Here's m and here's n. Okay? And we'll start with 0, 0. Well, the theorem is true for 0, 0. So we did the first step. Okay, because there's no index, so it's clearly symmetric in all the indices. Okay? Now we induce and 1, 0. That's also true. It has one upper index and 0, no lower index. So also true for this. Okay? So therefore we already did this case and this case and this case. So the induction is actually going up by lines. So going this way. So the induction is in P equal to Pm plus n. Going up in this direction to cover our representation. So now we go up to here. Then this guy is 1, 1. Well, that's also true. So this proof, you see, is very easy up to a certain point. Now, you come to the first non-trivial one. Okay? Which is, you come to this guy, 2, 0. So this is okay, but this guy, 2, 0. So this guy, let me call it phi. It has two indices, and I will abuse notation. Here I use I and j. But here just two upper indices, both I will call ij. And we now define the anti-symmetric part, the symmetric part, as phi ij plus phi ji, and the anti-symmetric part as phi ij minus phi ji. Okay? Now, So this is clearly symmetric and this is clearly anti-symmetric. That is to say phi ij is equal to phi ji. Or if you like, we can introduce some other notation. We call this, well, let's call this psi ij. Let me call it sij and this aij. So Sij is clearly symmetric and Aij is clearly anti-symmetric. Okay, so I've taken this representation, split into two pieces, right? It's split into two tensors. But this tensor, the theorem works. So you see the theorem is, this is called theorem by checking, proof by checking case by case. How about this? Well, it looks like the theorem fails. But I have the epsilon symbol. I can call this a new tensor T sub k. And for this tensor, it's already this case. So it's reduction. You know, there's a joke about mathematician. It's reduction to a previous case. Once it's reduced to a previous case, then it's okay. So you see it's reduced to a previous case. And so the 2, 0 case is okay. And the 0, 2 case is also okay. So then you have to, the 1, 1 case. The 1, 1 case is a tensor with one upper index and one lower index. The theorem is also true. It's symmetric in the upper and in the lower. So you prove this. Okay? So you just have to keep on going. So I've let you finish this proof as an exercise. I've done the difficult part. Well, that was a joke. I've done the easy part. Okay. Now, the other remark is that, well, the proof is very easy. You know, it's standard. So as an exercise, finish the proof. The next remark is that at each step, we can render the tensor traceless. Okay? So what does that mean? Suppose I have a tensor example. So it's best to explain by example. Suppose I have a tensor with 2 upper indices and 2 lower indices. So by the theorem that I just proved, we can, this is symmetric in interchanging ij, it's symmetric interchanging kl. So the trace, I can set to, the trace is defined as tiijl. So I set I equal to k and sum. And so this is a smaller tensor, which I call tjl. Okay. So, and then I have another trace, which is tjj, which I can call t. Okay. So, and it doesn't matter which of these two indices I sum. I can sum I with k, or I with l, or j with k, and j with l, because it's symmetric. So there's only one possible trace. So these are the two possible traces. Well, so then you can check the theorem is that you can always make this tensor traceless. And the way you do this is the obvious one. You take this tensor and then you subtract all its traces. You just subtract. So minus 1/5 delta ik tjl plus permutations minus plus 1/20 delta ik delta jl plus permutation times t. Okay? So you subtract out the two traces. You subtract out all the traces in all possible combination. So the important thing here is conceptually, you should understand that you can always do it. That these 5 and 20, that's irrelevant. I mean, that's for the, I mean, if you're building a bridge or something using SU3, you may have to worry about the 20. But if you're not, you probably don't need to know about the 20 and the 5. So, but the 5, I mean, that's combinatorics. So the way you check, you can check this if I set two indices equal and take out this, it's just going to end up being 0. Okay? Is that clear? So that's proved by one example, which is generally good enough in theoretical physics. Okay. So, of course, you can try to prove it in general. Okay? So, what is the bottom line of all this? The bottom line is that we proved that the irreducible representation, we have classified all the irreducible representations of SU3. The representations of SU3, irreducible representation of SU3 is symmetric traceless tensors. Okay, so now we can calculate what are the, you would want to know what are the dimension of these symmetric traceless tensors. Okay, so we can derive a formula. So I'm almost running out of time, but for the next 5 minutes, 5-10 minutes, I'll derive a formula for the dimension. Okay, so you talk to Gelman would say, don't waste time deriving this formula. I won the Nobel Prize with SU3 by just counting on my finger. So you can see, for all the simple cases, you could just count on your finger. It's almost trivial. So we already did 2 cases. We know that psi I is 3-dimensional because I takes on 3 values. Psi ij, since it's traceless, is 3 squared minus 1, is 8-dimensional, and so on. And Gelman's Nobel Prize winning one was that he counted this guy. Okay, the thing with 3 symmetric thing, and it turns out to be 10 dimension. And that won him the Nobel Prize, this calculation. Or at least it's part of the Nobel Prize. Okay, so when you know what you're doing, when you have the right idea, you don't need the general formula. But since we're in a group theory course, we should derive the formula. Yes? Sorry?
5 in your calculation, 20, connected to the 10.
Maybe at some level, yeah. Maybe at some level. Because, you know, I mean, all these numbers have to do with 3 minus 1 plus 1 and so on. Well, I can tell you this, whether it's connected to 5 or not. It's connected to 1, 2, 3, 4, 5. Okay. Okay. So let's calculate dimension. So I already said, Gelman said he just used his finger. But let's do the poor man's way. The poor man's way just basically counting on the finger. This would be the Feynman, Landau. I think Landau is very much my idea of a poor man. Okay. So you take a tensor, and now first let's do a baby case. Okay? And let's take m indices. And of course, it's all symmetric. So let's do it. We do the first baby step. So this is the poor baby, not poor man. It's supposed that I is too complicated for us to do I equal to 1, 2, 3. Let's just say I can only be 1 and 2. Then we have 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1. Them as 2, 2, 2, 1, 1, and so on, right? So finally, S 1, 1, 1, 1, 1. But if I have m of these, there are obviously m plus 1 possibilities. So that's the answer. There are m plus 1 such tensor. And now we do a next step. Now we let I equal to 1, 2, 3. So now the tensor is S. In general, there will be a bunch of 3s, but then there will be all these x's here, where x could be either 1 or 2. That's the notation. But there are k of these, okay? K x's. Each one of them could be 1 or 2. But we just proved here that there are m plus 1 possibilities. So there are k plus 1 possibilities. But this k can go from I could be 0 or m, right? So you just sum this as k equal to from 0 to m. And here you have to use Gauss summation. And you find that this is m plus 1, m plus 2. So now we just make a quick check. For m equal to 1, this is 1/2 2 times 3. It's 3, so that's correct. M equal to 2, it's 1/2 3 4. It's 6. And that's correct because you see a 2-index tensor that's symmetric has 6 indices. And you know this because of the moment of inertia for the students. I remind you. But there's some, I don't know, in some mechanics course, there's some, I learned that it was somehow 6. Okay. All right. So now we do SU3. This is just in which we only have all the upper ones. We now do the ones with the, including the lower indices as well. Okay. So I know it's almost time. So let me finish this calculation. So there are m upper indices and n lower indices. Well, that's very easy. From here, it's just 1/4 m plus 1, m plus 2, n plus 1, n plus 2, right? Because that's the number of possibilities for these guys and number of possibilities for that guy. But we forgot one thing. We still have to take out the trace. We must take out the trace. But to take out the trace, since this is symmetric, it doesn't matter which one we set equal and trace over. So we might as well set the last one equal, k, j1, jn minus 1. So we want to subtract out the trace to make it traceless. Another way of saying this is that we want to set this equal to 0. But we want to know, so these are a lot of constraints on the tensor, okay? So number of conditions. So we want to know what the number of conditions is. Number of conditions. But this is just the number of components of m minus 1, n minus 1. Right? This is just a tensor with m minus 1 indices and n minus 1 indices. Last time I explained that when you take the trace, the indices eat each other and disappear. Okay? So therefore the number of conditions just equal to, we just copy from here. We don't have to calculate. It's 1/4 m times n plus 1, n times n plus 1. We just shift m and n by 1. And now we subtract. Okay? We subtract this line from that line and we get the components. And so the dimension is that's the final formula. Okay, so we found the formulas for the representations of SU3. So we now can make a table. So 1, 0, you can check. You know, it's 1/2, 2, 3 is 3, and 1, 1 is 8, and 2, 0, 3, 0, and 2, 1, 2, 2, and this is 6, 10, 15, and 27. So I already said this is partly Gell-Mann's Nobel Prize. He calculated the 10. Okay. So I will close the lectures by mentioning this 10. So at the time, there were 9 particles known experimentally. There are 9 so-called baryon resonances. Experimentalists have discovered 9 particles whose masses are different but similar. And Gell-Mann looked at this list, and Gell-Mann said, well, I know a lot of math, but what I know is that there's no 9. And the closest number to 9 is 10. So Gell-Mann predicted there must be a 10th particle. And since he knows SU3, he knows the isospin, he knows the charge, right? We know the formula for the charge. So he predicted a particle which he named the omega minus, because the omega was from alpha to omega. Omega was the end of physics or something. So he predicted this, and this was the famous omega minus experiment. When they turned on the bubble chamber, they found the omega minus. So that was Gell-Mann's great triumph. So the 27, there's also an interesting story, which I'll tell you next time. The 27 does not involve Gell-Mann, but it involves Feynman. So I'll tell you Feynman and the story of Feynman in 27 next time. Okay, good. Thanks. Thank you, and next week.